Hello, I'm Tejashree, a PhD student working with Professor Rajesh Sundaresan in the Department of ECE. Today, I'm going to talk about oral cancer screening using AI, an initiative of the AICOE. Let us delve into the problem statement. India contributes to about one third of the global burden of oral cancer, and it is among the top three cancers in the country. Screening oral cancer at early stages translates to better care, cure, and prevention. Due to the prevalent practices that are there, especially in the rural masses, where people are more habituated to chewing tobacco, areca nut, etc., makes them prone to the diseases of the mouth. In order to cater to these masses with lower accessibility to quality healthcare, oral cancer screening is essential to pick up early stage cancers to improve the quality of life of patients. Now let us understand the role of AI in oral cancer screening. Visual examination by a trained clinician is a usual practice in screening. To screen large populations, technology has been made use of as there is a shortage of trained clinicians. In the recent past, different kind of imaging such as white light, fluorescent, embedded with smartphones have been experimented to image oral cavity, and then such images would be transported to a remote specialist via networks, and generally this process used to take a week or so, and by this time the patients would be lost out of reach. As a solution to all these problems, embedding AI into oral cancer screening is essential. How it works: we embed trained AI models with a mobile app through which we capture images of the oral cavity of subjects. AI model works on these images and produces results on each of these images within a few seconds, and care can be provided to the patient according to the analysis. Additionally, these images are also sent to centralized and secure servers. As of now, we are training AI models to classify images into two categories: suspicious, non suspicious, and high risk versus low risk. Before we proceed further, let us have some understanding of the labels. Every image that is captured by a smartphone is shown to a trained clinician and obtained a label. There are 8 labels, which are normal, benign, TPK, HL, OSMF, OLP, NHL, cancer, which are further classified into suspicious or non-suspicious and high risk or low risk categories. TPK to cancer fall under suspicious categories as they are either malignant or orally potential malignant disorders. And the risk-based classification is mainly based on the potential to transform into malignancy. Also, we have another label called as non-diagnostic, which is primarily given to those images from which no diagnosis can be made. That is, all the poor quality images are given non-diagnostic label. We have not included such images for the training purposes. Now, let us look at the development of AI model. We experimented with both CNN as well as transformer-based models such as Inception, EfficientNet, VIT, Mobile VIT, Fast VIT, and also distillation of VIT. We also experimented with some of the image quality analysis filters such as Clip IQA and Nike. Segmentation methods such as bounding boxes and SAM were used to augment the current dataset. We also tried with random flip, random rotation, and motion blur augmentations to make the models robust. The initial dataset which we started working with had 1344 train images, 412 validation images, and 422 test images. All these images were obtained from the Biocon Foundation. We are currently working on another large dataset on which we are continuing our exploration. Let us have a look at some of the sample images. On the left hand side, we have examples of non-suspicious images, whereas on the right hand side, we have examples of suspicious images. On the right top, we have a high risk suspicious image, whereas on the right bottom, we have a low risk suspicious image. Now, let us have a look at some of the results that we obtained by training 100 mobile VAT version 2 models, and these are the main performance metrics. Also, the performance of the best model out of the 100 models is as follows. It had an accuracy of 90.52%, sensitivity of 94.53%, and specificity of 86.88%. And all of these results are for suspicious versus non-suspicious classification. Efforts are also made to bring about similar results in high-risk versus low-risk classification, as well as a combined suspicious plus risk classification. Coming to model size and number of parameters of the models, VIT B16, which is a base model, has about 86 million parameters. Mobile VIT version 2, which has produced the best results, is the second version of mobile VIT. Mobile VITs are generally lightweight general purpose VIT for mobile devices, whereas mobile VIT version 2 is a combination of both CNN as well as transformer, and it was constructed by replacing the multi-headed self-attention in mobile VIT with separable self-attention and has about 4.38 million parameters. The fully trained mobile VIT version 2 model occupies a size of about 16.9 MB, and this can be integrated optimistically in any mobile app of size 50 MB. Coming to the future steps, we intend to perform multi-reader multi-case analysis for our developed models and also to prove that AI model is not worse than, or in case if it is better than, any of the human readers for high risk versus low risk classification, as well as the suspicious versus non-suspicious classification by statistical methods. Also, we intend to obtain a Class B certification for the developed models for large-scale usage. Thank you for listening.